Violin in a Fire. It begins in a cold workshop outside Augsburg in early 1943. Metal dust hangs in the air. Lamps stutter each time a distant bombing raid shakes the ground. A young engineer named Dieter wipes grease from his hands. He studies the half-assembled Panther hull in front of him. He knows the lines are beautiful. He also knows the machine is late. He remembers the first time he saw the Panther drawings. The glacis plate sloped like a blade, a lesson learned from the Soviet T-34. The 75mm gun promised range and velocity that could kill an enemy tank from a distance. But he also saw the parts list. Long weld seams, interlocked plates that demanded thousands of hours of precise machining, a 7-speed gearbox that required tight tolerances. The machine needed nearly twice the machining hours of a Panzer IV, about 1,500 hours versus roughly 800. Dieter thought then, this is a grand piano score being handed to a street band. He felt the gap between the design's purity and the shop's reality. It was like building a violin during a fire. The fire was Germany's collapsing industrial base. It showed up in small ways at first. Dieter's shift started before dawn on a concrete floor that was always damp. Coal trucks missed deliveries twice a week because Allied bombers had cratered the rail lines. When trains did arrive, they brought steel plate with edges warped from rushed rolling. Dieter and his crew would spend hours grinding the plates back to tolerance. The hull on his stand had chalk notes that read, "Rework weld seam 4 hours." Each interlocked seam, designed to spare welds and add strength, added minutes. The minutes added up to days. Outside, the sirens wailed almost every night. The shop's windows were taped in crude X patterns. Foremen faced a choice: stop work and lose another hour, or keep going and hope the raid missed Augsburg. In February, a blast wave showered glass onto the assembly area. No one was hurt, but they lost 2 days covering the roof with tar paper. Dieter marked 31 lost labor hours from that incident alone. His monthly reports demanded those numbers. Then the fire showed up as critical shortages. High-grade iron ore from Sweden was harder to get. Manganese from Ukraine was gone. Recycled scrap arrived in larger, rustier piles. The steel sometimes had tiny inclusions that caused weld spatter. Dieter and a veteran welder named Ernst traced the seams, their helmets flickering as voltage dropped during power rationing. They kept count of their rods. Even welding consumables were rationed. The most critical shortage, the one that stopped the line cold, was ball bearings. A single Panther needed dozens of precision bearings for its gearbox, final drives, and suspension. They were the rolling heart of the machine. In March, a shipment of bearings arrived late and incomplete. Assembly of the final drives halted. Dieter walked the line and saw a row of half-built Panthers stalled at the same stage. He heard the plant manager on the phone, his voice tight, requesting substitutions. "Use bushings where you can," the manager said. Dieter knew what that meant. He later tested a bushing swap in a final drive and heard the faint grind of metal on metal where a bearing would have rolled smooth. He wrote in his log, "Functional but reduced service life is likely." The memo went upstairs. No answer came back. The line moved on. In the break room, the men talked about the Schweinfurt raids. Everyone knew the name. The city was the heart of German bearing production. Factories like Kugelfischer, Vereinigte Kugellagerfabriken, and Fichtel and Sachs collectively made nearly 2/3 of the nation's total output. The Americans came for it on August 17, 1943, and again on October 14th, a day the bomber crews called Black Thursday. The raids were costly for the Allies, but they temporarily cut production by more than 1/3. Armaments Minister Albert Speer would later admit that a sustained campaign against Schweinfurt could have crippled the war machine in months. But the campaign wasn't sustained. Germany dispersed production, got what it could from neutral Sweden and Switzerland, and the lines started moving again. But the bearings that reached Dieter's factory were never quite the same quality or quantity again. The violin was being built with borrowed strings. The German engineering philosophy was a relentless pursuit of quality. When British engineers inspected a captured tiger eye, they were impressed by its meticulous construction. But they also saw its weakness. It had over 26,000 parts and took 300,000 man-hours to build. It was a masterpiece that couldn't be mass-produced. The Panther was simpler than the Tiger, but it followed the same philosophy. Dieter saw the contrast on the radio reports from the Eastern Front. The announcer spoke of Soviet T-34s appearing in waves. The T-34 was the opposite of the Panther. It was brutally simple. Its armor was roughly welded. Its interior was cramped. But it was reliable, easy to repair, and designed for mass production from the start. Soviet factories, relocated to the safety of the Ural Mountains, pushed out hundreds of them every week. By the war's end, the Soviets would build over 80,000 T-34s. Germany would build about 6,000 Panthers. It was a ratio of more than 10 to 1. Dieter wrote the numbers in his notebook. The violin is rare, the drums are many. The engine was another point of contrast. The Panther was powered by a Maybach HL 230, a 23-liter V12 gasoline engine. It was a marvel of compact power, delivering almost 700 horsepower. But it was thirsty, complex, and prone to overheating. Early versions of the engine in the heavy Tiger tank, the HL 210, were found to be underpowered and were rushed into production, forcing crews to run them below maximum RPM to ensure they didn't fail. The Maybach gasoline engines also made the tanks vulnerable to fire. The T-34, by contrast, used a rugged V2 diesel engine. It was less powerful, but it was more fuel-efficient and less flammable. One morning, a flatbed arrived at Dieter's factory with only 3 of the 6 expected Maybach engines. 3 Panther hulls would have to wait. The foreman warned that rubber hoses for the fuel lines were also in short supply, so every cut had to be exact. The fire meant people burned out, too. Skilled toolmakers were drafted and sent to the front. The factory hired teenagers, foreign forced laborers, and refugees with minimal training. Dieter set up short courses on how to read blueprints and how to dress a grinding wheel. He simplified instructions. He knew the machine demanded finesse his workforce couldn't consistently provide. This meant more rework, more wasted material, more hours lost. In mid-1943, the Panther program issued 14 design updates in a single month. Each update forced a pause as jigs were realigned and fixtures were reworked. Dieter felt like a conductor trying to keep tempo while new sheet music kept arriving mid-song. One evening, he watched a finished Panther roll out for a test. The driver eased it forward, the Maybach's growl filling the yard. The suspension glided over a rough patch of cobbles. It looked like a promise kept. Then a mechanic signaled a stop. A hydraulic line was weeping at a fitting. The test halted. They pulled the machine back inside. Dieter felt frustration and relief at once. The flaw was found here, not at the front. He kept a small notebook of quotes and numbers. Fuel cut by 1/3. Bearing deliveries delayed 14 days. Design update 15 in 1 month. Weld seam rework 4 hours. The notes were not complaints. They were the data of industrial war. He was an engineer. He wanted to understand cause and effect. He saw how the pursuit of perfection, the love for the elegant solution, became a weakness in a war of attrition. Engineering is choice under constraint, he wrote. Our constraints are now a fire. He tried to keep his sentences simple in his notes. Voltage low, weld porosity risk. Bearing shipment missing. Fuel ration cut again. He wanted future engineers to hear the rhythm of constraint, to see that the Panther's elegance did not float above the war. It sat in it. Near the end of the year, he wrote, We could design excellence. We could not escape reality. That was the lesson of the violin in the fire. A machine can be brilliant, but if the foundry is cracked, the rails are bombed, and the workforce is green, brilliance stalls. The Panther was a masterpiece of design born from a starving economy. It was a violin, played beautifully but briefly, in the middle of an inferno. Takeaway: the Panther's story shows the collision between engineering perfectionism and the brutal logic of industrial warfare. German designers created a technically superior tank, but they couldn't overcome the realities of resource scarcity, Allied bombing, and an enemy who chose quantity over quality, and ultimately won the numbers game. Materials evaporate. By early 1943, Dieter notices that the shop's steel racks look thinner. Rolls of high-grade plate arrive with more rust bloom. The flow of ore has changed. Germany has lost roughly half of its pre-war sources of high-grade iron ore. Swedish deliveries continue, but not at the volume heavy armor needs. Manganese from Ukraine is gone. Synthetic rubber output never meets its promises. The material story is one of subtraction. The Panther's bill of materials reads like a shopping list from a shrinking store. Thick plate for the glacis and side armor, alloy steel for gears, copper for wiring, aluminum for certain housings, ball bearings by the box. Each item meets a narrowing supply. Dieter starts tracking delays in his notebook. Ore, late, bearings, short, copper diverted to aircraft. Each entry is a quiet alarm. In the foundry, the melts change. Steel batches include more scrap to compensate for scarce ore. Dieter and the metallurgist, Frau Keller, test the ingots for inclusions. Tiny slag pockets become more common. Those pockets can become crack starters. Keller adjusts flux ratios and hopes. She mutters, "We are making soup from leftovers." Dieter writes the line down because it captures the mood. Soup from leftovers is not how you feed a precision machine. Ball bearings become the sharpest pain. The Panther's final drives and transmission need dozens of precision bearings to handle torque and speed. After Allied raids on Schweinfurt, deliveries drop sharply. Speer orders redesigns to use simpler bearings or none where possible. Dieter receives drawings that replace certain bearings with bushings. He runs a bench test and hears a faint grind where once there was a smooth roll. He notes reduced service life and sends the results upward. No answer returns. The redesign holds because there is no alternative. Then comes the missing element no redesign can hide: molybdenum. It keeps armor from shattering. When supplies from Portugal disappear, chemists substitute vanadium. The steel hardens but loses toughness. British tests in 1944 show late Panther armor cracking or even shattering like glass when hit, even if the shell does not punch through. Dieter hears rumors of these tests and worries that every batch of plate might be a coin flip. Rubber shortages hit the suspension. The Panther's road wheels and track pads rely on synthetic rubber. Output from Buna plants never matches projections. Dieter sees wheels arriving with harder compound substitutes. Harder rubber cracks in cold. He logs a note: "Expect more wheel swaps in winter." It is an engineer's attempt to anticipate a frontline complaint. Copper and aluminum divert to aircraft factories. Tank wiring looms get thinner. Some connectors switch to steel, adding weight and corrosion risk. Dieter edits assembly instructions to include extra grease on those connectors. He knows grease is also rationed. He writes it anyway because omission would be worse. Fuel is its own material. Allocations fall by about 1/3 between early 1943 and mid-1944. Generators in the plant run on reduced schedules. Power cuts arrive with no warning. Welders lose arcs mid-bead. Machining stops mid-pass. Dieter watches a milling machine freeze on a gear blank, leaving a gouge that scrapped an hour's work. He writes a report linking power instability to increased scrap. Management files it. Nothing changes, because fuel does not appear from paper. Design updates respond to material loss. Dieter sits with a set of revised hull drawings that trim a few millimeters from non-critical plates to save steel. He calculates the weight reduction and the potential change in ballistic resistance. He marks minimal impact if weld integrity maintained. He signs off because the alternative is no hull at all. The violin loses strings, but the song must play. The human element shifts with the materials. Skilled toolmakers gone to the front means more rework, more mistakes, more wasted steel. A mise-cut plate cannot be uncut. A bad heat treatment ruins a gear batch. Each error burns scarce materials. Dieter responds by writing clearer instructions and adding checkpoints. He tries to stop losses before they happen. Supply trains become unreliable as Allied bombing intensifies. A shipment of manganese arrives 2 weeks late and half short. Keller adjusts alloy recipes again. She tells Dieter, "We are now writing a new book of steel." He nods. The Panther's metallurgy, once standard, becomes an improvisation chapter by chapter. Factories adapt. They store more scrap for remelt. They scavenge copper from older equipment. They send workers to tear down damaged machines for usable parts. Dieter approves a plan to reclaim bearings from damaged Panther gearboxes returned from the field. He inspects the salvaged parts. Some are usable. Many are pitted. He labels them by risk and sends the best back into circulation. It feels like triage in a hospital short on supplies. Dieter reads field reports about Panthers stranded by seized final drives. He links those failures to the bearing shortages and bushing substitutions. He writes a memo recommending priority, bearing allocation to final drives and transmissions over secondary components. The memo goes to Spear's office via the plant manager. He never hears back. He suspects the answer is obvious. There are not enough bearings to prioritize anything. Meanwhile, the Allies pour steel into their own factories. Soviet T-34 production runs on abundant manganese and simpler designs. American Sherman plants draw from vast ore and rubber reserves. Dieter sketches a comparison in his notebook. Panther, complex material hungry. T-34, simpler, tolerant of rough steel. He draws 2 boxes to represent output. A small box for Panthers, a large one for T-34s. It is a visual he cannot ignore. By war's end, the ratio will sit around 1 Panther for every 8 T-34s, and 1 Panther for every 8 Shermans combined, even before counting British and Canadian armor. The shortage of materials also affects morale. Workers see the thin bins. They know when a shift waits idle because bearings are missing. They feel the strain of reworking parts because the steel batch had inclusions. Dieter holds briefings to explain why the Panther needs certain alloys and why substitutions are risky. He hopes understanding will keep quality up even when frustration rises. He quotes his father, "Measure twice, cut once, even if the wood is scarce." The workers listen. Some nod. Some look past him at the empty bins. Bombing raids add another subtraction layer. Roofs patched with tar paper let rain seep onto stored plate. Rust blooms faster. Trucks reroute around cratered roads, arriving late with partial loads. A week's production schedule becomes a guess. Dieter builds contingency charts. If bearings arrive Tuesday, assemble final drives. If not, shift to hull welds. The chart looks like a war plan because it is one. All these shortages shape the Panther itself. The tank that rolls out in late 1944 is still lethal at range, but it carries the marks of scarcity. Some batches have weaker final drives. Some have wiring with more steel. Some have hulls welded under low voltage, risking porosity. The machine is brilliant on paper and brittle in places on the ground. Dieter does not romanticize the struggle. He writes plainly, "Materials evaporate, we redesign, we lose time, we risk quality." He respects the designers who drew the Panther's lines. He respects the welders and machinists who adapt daily. He also knows that without steady ore, rubber, copper, and bearings, even the best design slides toward failure. In a rare quiet moment, Dieter walks the yard and runs his hand along a finished Panther's glacis. The armor is cold and smooth. He thinks about the ore mines that fed this plate, the rail lines that carried it, the smelters that refined it, the welders who joined it. He thinks about the ones missing. He hears distant anti-aircraft guns and remembers Keller's line about soup from leftovers. He wonders how long they can cook. Takeaway: the Panther's promise depended on steady streams of ore, alloys, rubber, copper, and bearings. When those streams thinned, Germany redesigned on the fly, burning time and risking quality. Materials are the hidden architecture of any machine. When they evaporate, the design has to shrink with them. Fuel and hands run out. Every month brought new constraints. Fuel allocations fell by roughly 1/3 between early 1943 and mid-1944. That cut hit every motor and every shift. Generators in the plant ran on reduced schedules. Night crews worked under blackouts with rationed kilowatts. Dieter kept a chart on the wall. Hours of power promised versus hours delivered. The gap widened each week. Fuel is more than motion. It is electrical stability, forge heat, and compressor air. When power dipped, welders lost arcs. Machinists lost a pass halfway through a gear tooth. The Maybach HL 230 engine blocks waiting on benches did not care about ideology. They cared about clean cuts and steady feeds. Dieter tracked scrap rates. Each power sag created gouged gear blanks and porous weld beads. Scrap climbed by single-digit percentages that ate whole days of work. Copper and aluminum, the blood of wiring and light housings, diverted to aircraft. Messerschmitt plants had priority. Tank wiring looms arrived thinner, with steel connectors substituted where copper once sat. Steel adds weight and corrosion risk. Dieter wrote extra grease instructions into the assembly notes. He knew units in the field might not have grease to spare. The redesigns were not elegant, they were survival. Skilled hands ran out alongside fuel. Draft notices pulled toolmakers and machinists to the front. The factory filled slots with teenagers, foreign forced laborers, and refugees with little training. Dieter set up crash courses on the Panther's weld angles and on how to dress a grinding wheel to hold a clean edge. He broke procedures into shorter steps and simplified language. Even so, error rates climbed. A mise-set jig could ruin an 80mm glacis plate. A rushed hole could wreck a gearbox housing. Every mistake consumed material that was already scarce. In some plants, foreign forced laborers and prisoners of war made up close to 40% of the workforce. Sabotage slipped into the assembly line. A loose washer dropped into a gearbox. A bolt left fingertip tight inside an oil pan. The tank would pass a short factory test and then destroy itself 50 miles toward the front. Dieter never knew which failure was a mistake and which was resistance. Both consumed the same precious hours and parts. Statistics from Speer's ministry talked about rationalization. The idea was to cut variance, standardize parts, and drive volume. For the Panther, rationalization collided with shortage. Bearings from Schweinfurt came in late and light after raids. Dieter saw weeks where final drive stations stood idle because a single bearing size was missing. He counted 20 hulls stalled at once, 20 hulls that could not move to engine install because one part bin sat empty. Fuel cutbacks forced scheduling gymnastics. Dieter proposed staggered shifts to avoid the lowest voltage hours. Management agreed, and crews rearranged sleep around curfews and air raid sirens. Some nights workers slept on cots beside the machines because travel after dark risked arrest. The plant became both workplace and barracks. Blackout curtains hung heavy. Air raid wardens patrolled with flashlights while men tried to keep welding heat on target. The labor shortage showed in weld quality. Experienced welders could keep bead profile consistent even when voltage sagged. New welders could not. Dieter increased inspections on critical seams, glacis interlocks, turret rings, and suspension mounts. He logged porosity incidents and rework times. Rework meant grinding out bad metal and laying new bead, hours added, rods consumed, fatigue increased. He wrote a memo linking low voltage to porosity on a specific shift. Procurement replied with a thin note, fuel ration unchanged. Tooling suffered too. Spare parts for milling machines and lathes were harder to get. Bearings for the machines themselves were short. When a spindle bearing failed, a machine could sit idle for a week waiting on a replacement. Dieter authorized cannibalizing less critical machines to keep key ones running. It was the same pattern as cannibalizing Panthers for parts in the field, only happening in the factory first. The human cost was visible. A veteran machinist named Vogel was drafted. His replacement was a 19-year-old who had never run a horizontal mill. Dieter spent an entire shift teaching him how to set up a gear blank and check backlash on a test fit. The teenager learned fast but lacked the feel that comes from years at a machine. Production slowed while the learning curve burned fuel, power, and patience. Outside reports reinforced the pressure. Frontline units asked for Panthers with reliable transmissions. They wanted engines that could run more than 100 kilometers without seizing. They sent back stories of final drives failing on road marches. Dieter knew the link: missing bearings, rushed heat treatments, undertrained hands, and a power grid that flickered every night. He also knew commanders did not want excuses. They wanted tanks that moved. Fuel scarcity reached absurd edges. Forklifts waited idle because their fuel allotment was gone for the week. Men pushed pallets of track links by hand. A delivery truck with copper wiring showed up with half its load missing, siphoned on the road. Guards added extra locks. Theft was a symptom of scarcity, and every missing crate became another design change or delay. Copper shortages led to substitutions in the Panther's electrical system. Starter motors used less copper windings and ran hotter. Wiring harness insulation quality dropped. Field reports later noted cracked insulation and shorts after rain exposure. Dieter wrote guidance to apply sealant where possible. Sealant was also rationed. Workarounds piled on workarounds. Labor inputs became quantifiable pain. Early Panther builds demanded upward of 100,000 to 150,000 labor hours per tank across the chain. Later improvements pushed that down, but the Panther still consumed roughly double the labor of a Panzer IV and several times that of a T-34. Dieter watched man-hours sink into rework caused by power cuts and green workers. He scribbled ratios. Hours lost to rework this week, 8%. Bearings missing, 20 hulls idle. These were the numbers behind the propaganda posters that still promised victory. The plant tried to automate where it could. Simple jigs replaced skilled eyeballing for certain welds. Standardized templates cut setup time for suspension arms. These helped, but they could not erase fuel and material shortages. A jig still needs steady power. A template still needs a trained hand to clamp and check. Dieter sometimes stepped back to compare Germany's situation to its opponents. The Soviet Union moved T-34 production east, away from bombers. Their factories ran on large coal supplies and simpler designs. American plants built Shermans with vast oil, copper, and aluminum resources behind them. Germany was trying to make a precision machine while running on reduced fuel and shrinking labor. The ratios were unforgiving. 6,000 Panthers total against roughly 50,000 T-34s and almost 49,000 Shermans. Fuel and hands shaped that gap as much as steel. He did not romanticize the shortages. He wrote plainly, "Fuel reduced by 1/3. Power cut 8 hours this week. Labor, 20 skilled men drafted, rework time up 10%. These were facts for engineers, not slogans. He wanted future builders to see how logistics set the ceiling for design. In late 1944, the fuel story worsened. Allied bombing of refineries and railroads cut deliveries further. The plant stored drums of low-grade fuel that fouled engines. Generators clogged. Maintenance crews spent hours cleaning filters instead of making tanks. Dieter noted the irony. Precious labor hours spent fixing the machines that were supposed to make the machines. Takeaway, fuel and skilled hands are the invisible scaffolding of a tank program. When fuel falls by a third and trained labor thins out, every weld, gear, and test slows. For engineers and architects, the lesson is blunt. Design ambition dies without energy and expertise to carry it. Panzer workhorse benchmark. Before the Panther, the Panzer IV set the production rhythm. The tank began as a support vehicle in the late 1930s with a short 75mm gun. By 1942, its Ausführung carried long-barreled guns and thicker frontal armor. The chassis stayed simple: flat plates, short weld seams, and leaf spring bogies with 8 small road wheels per side. That simplicity mattered to the factories. Machining hours ran at roughly half of what a Panther would later demand. Dieter keeps an old Panzer IV drawing pinned beside the Panther plans to remind himself what workhorse tolerances feel like. In the Krupp-Gruson plant at Magdeburg, foremen spoke of straight cuts and straight welds. The hull sides were rolled and cut with generous edge margins. Welds ran short and mostly straight. There were no long interlocks like the Panther glacis. Welders could lay bead at standard voltage without worrying about porosity spikes on slopes. When power dipped during winter rationing, the Panzer IV's joints forgave more. Rework stayed lower. The suspension told a similar story. Leaf springs and paired bogies could be swapped as assemblies. When a bogie cracked, crews on the line unbolted it and bolted a replacement. The Panther's torsion bars needed precise arm alignment and were harder to replace. Field crews noticed the difference. Panzer IV suspensions tolerated mud and ice better and took less time to service on a cold roadside. The gearbox, often the Zonrad fabric SSG 77, was simpler than the Panther's AK 7200. Fewer gears, fewer precision ground faces, and less demand on bearings. Plant notes from 1942 show machining times for a Panzer IV gearbox at roughly 1 shift versus multiple shifts for a Panther's. Final drives were more robust relative to vehicle weight. In field reports, Panzer IVs tended to reach the front and keep running. Panthers sometimes failed on the first long march. Weight stayed modest. Early Panzer IVs sat near 25 metric tons. Later variants with thicker armor approached 28. That lower mass reduced stress on tracks and bridges. Panthers pushed 45 tons. Tigers went higher. Dieter liked to say, "The Panzer IV sits light on the road," meaning fewer broken final drives and less track wear. His logbooks showed fewer returns to the factory for drivetrain overhaul compared to Panthers. Armor evolution on the Panzer IV was straightforward. Frontal plates grew from 50mm to around 80. Side skirts added defense against anti-tank rifles. The flat plates did not give the angled protection of the Panther, but they were easier to produce and repair. Crews welded patch plates in the field with basic gear. The Panther's sloped plates required more careful fit-up and heat control that field welders often lacked. Guns improved without overhauling the hull. The shift to the long 75mm KW K40 transformed the Panzer IV into a true tank killer. Barrel production stayed manageable. It did not require the tight tolerances of the Panther's high-velocity KW K42. Optical sights were simpler too, easing strain on specialized optical grinding shops that were already overworked. Production numbers reveal the effect. Germany built more than 8,000 Panzer IVs. Some months in 1943 saw outputs above 300 across all plants. Panthers never reached that monthly rhythm. Panthers topped out around 6,000 total. Tigers stopped under 1,500 combined. Panzer IV volume kept armored units supplied, while newer designs struggled with complexity. Material lists for the Panzer IV were kinder to a shrinking economy. Less high-alloy steel, fewer precision bearings, shorter welds, and looser tolerances on non-critical surfaces. When ball bearings from Schweinfurt fell short after Allied raids, Panzer IV lines slowed, but did not stall as sharply as Panther lines. Dieter remembered a week when Panthers sat idle waiting for one bearing size, while Panzer IVs kept moving with alternative suppliers and bushings that still met spec. Memoirs from shop foremen describe the Panzer IV as honest work. A fitter from Vomag wrote, 2 days to weld a hull, 1 day to dress it, and it runs. He contrasted that with Panthers. 3 days, and if voltage drops, start over. Crews in the field echoed the sentiment. A maintenance sergeant on the Eastern Front told a visiting inspector, Panzer IV will limp home. Panther is either perfect or stopped. Standardization helped. Many Panzer IV components carried over across variants, turret rings, portions of the suspension, and internal fittings. Tooling stayed relevant longer. Jigs and fixtures wore in, not out, because the design stabilized. The Panther received 14 design updates in 1 month of 1943. The Panzer IV saw far fewer disruptive changes, which kept throughput predictable. The Panzer IV is also the only German tank that stayed in production from the first day of the war to the last. Its chassis became a platform for everything: anti-aircraft wagons, assault guns, tank destroyers. It was the Toyota Hilux of the Wehrmacht, never glamorous, always running, always available for another role while the prestige machines stole headlines. Panzer IV production also benefited from dispersed manufacturing before bombing intensified. Multiple factories, Krupp-Gruson, Vomag, and Neiblingenwerk shared the workload. That spread diluted the impact when one plant took a hit. When Neiblingenwerk slowed after a raid, Magdeburg picked up slack. Panthers and Tigers, tied to fewer specialized shops, had less buffer. Dieter compared machining hours often. He logged Panthers at about 1,500 machining hours in early runs versus roughly 800 for a Panzer IV. Labor hours across the whole build could be double for a Panther. In a fuel and labor-starved economy, those differences mattered more than paper armor thickness. Each hour lost to a power cut hurt the Panther twice as much. Even with its simplicity, the Panzer IV was not free of strain. As armor thickened, the basic chassis approached its limits. Final drives wore faster, engines ran hotter. But the platform absorbed those changes without a redesign as radical as the Panther. That incremental approach matched the industrial reality better than the leap to a high-spec machine during a bombing campaign. Field anecdotes reinforce the workhorse label. In one unit diary from Kursk, a company reported 80% of its Panzer IVs operational after a week of fighting, while attached Panthers were down to half strength from mechanical issues and recovery delays. The Panzer IVs lacked the Panther's long-range dominance, but they were present in numbers and stayed moving. For engineers, the Panzer IV is the control in the experiment. It shows what German industry could do under stress: standardized parts, stable tooling, manageable weld sequences, and a drivetrain matched to weight. It also shows the cost of complexity when contrasted with the Panther that followed. Dieter's pinned drawing is not nostalgia. It is a reminder that reliability and volume are design choices. Takeaway: the Panzer IV set a realistic industrial baseline. Its straight welds, leaf spring suspension, simpler gearbox, and forgiving tolerances let Germany build thousands even as bombs fell. Against that benchmark, the Panther's higher performance came with a price in hours, bearings, and failures that the shrinking economy struggled to pay. Panther complexity. Inside the Panther program, the pressure was constant because the machine itself was complex. The Panther demanded roughly twice the machining hours of the older Panzer IV, about 1,500 hours versus around 800 in early runs. Its armor layout used interlocked plates and long weld seams that saved weight and improved ballistics, but added labor. Its 75mm KW K-42 gun offered long reach and high velocity, but the gun mount and recoil system needed tight tolerances. Each choice improved performance and increased manufacturing difficulty. The hull alone shows the equation. An 80mm glacis plate sloped at 55 degrees had to meet side plates without gaps. The interlock required precise milling and a controlled weld sequence. Weld too hot and distortion warped the fit. Weld too cold and porosity weakened the joint. Dieter wrote sequences on the wall. Clamp order ABC preheat to target. Pause between passes. These steps slowed throughput but protected integrity. The suspension was another layer. Torsion bars gave the Panther a smoother ride and better gun stability than older leaf spring layouts. But each torsion arm had to align within millimeters, or the bar would twist and crack. Setting those arms took time. The road wheels used paired stations. Misalignment created uneven load, leading to wheel failures in service. Dieter timed how long alignment checks added. 40 minutes here, an hour there. The minutes became days across a production month. The gearbox, the AK-7200, was a design point of pride and pain. 7 forward gears and double planetary steering gave the Panther agility, but the gearbox needed dozens of precision ground gears and quality bearings. After the Schweinfurt raids, bearings arrived late or short. Substituting bushings increased friction and heat, shortening life. Field reports later noted gearboxes failing within the first 100 kilometers for some batches. Dieter linked those failures to material substitutions and rushed assembly under power cuts. The final drives were a known weak spot. Spur gears took high loads from the Panther's weight and the torque of the Maybach HL 230. They were sensitive to heat treatment and to bearing quality. A single wrong hardness could mean chipped teeth. A single flawed bearing could seize the drive. Dieter pushed for stricter checks on final drives, but time pressure and material shortages cut into those safeguards. The root of the final drive problem was baked in. The gears were drawn for a 30-ton class vehicle. Hitler and the Armor Committee kept adding armor and features until the Panther weighed around 45 tons. The final drive housing never grew to match the added load. A heavy tank walked on the ankles of a light tank, and the ankles cracked. Compared to the Soviet T-34, the Panther's design offered better optics, a more precise gun, and thicker sloped armor. But the T-34 used simpler welds, fewer machining operations, and looser tolerances that factories could hit even with newer workers and rough steel. Soviet factories produced hundreds of T-34s per week. German plants often made Panthers in tens per week. Complexity set a ceiling on output when labor and materials were thin. Design updates added churn. In mid-1943, 14 updates hit in 1 month. Each forced the line to stop, retool, and restart. A change to the turret ring machining step added an hour per unit. A small adjustment to the gun mantlet contour required a new jig and scrapped the old one. Dieter taped each update to a board and marked completion dates. The board looked like a conductor's score, each change another bar to hit. Weld length mattered. A Panther hull carried many more meters of weld than a Panzer IV. One estimate put total structural weld length at roughly 2 to 3 times the earlier tank. Longer welds mean more filler metal, more rods, more chances for porosity. Under power rationing, voltage sag increased defects. Dieter logged porosity incidents rising during low-voltage nights. Rework consumed rods, grinding wheels, and hours. Optics and sighting equipment added precision work. German optics were excellent, but grinding lenses and aligning sights were skilled tasks. When experienced optical workers were drafted, quality risked dropping. Dieter noted more rechecks on sight alignment and occasional returns from the front citing fogged or misaligned sights. Each return meant repair time and shipping, more drag on a program already late. The engine bay was tight. The Maybach HL230 fit, but only just. Cooling lines, fuel lines, and electrical harnesses crowded the compartment. A slight deviation in routing could cause chafe and leaks. Dieter wrote routing diagrams to prevent contact points. Under rushed conditions, shortcuts crept in. Some field Panthers showed fuel leaks and overheating traced to cramped runs and quick fixes. Weight management was part of the complexity story. The Panther sat around 45 metric tons. Weight crept up with armor changes and added equipment. To keep mobility, designers leaned on the high-velocity gun and sloped armor rather than thicker plate. But sloped armor required more careful cutting and fitting. Simple flat plates would have been faster. Sloped interlocks saved weight but cost time. The turret added its own challenges. The traverse gear had to mesh smoothly under load. Any burr or misalignment meant binding. Turret balance depended on exact gun and counterweight specs. Changing one component often cascaded into rebalancing. Dieter saw a batch where a slight variance in gun mount machining forced extra shims and hand fitting. It slowed turret assembly for a week. Powertrain integration tied all of this together. A Panther's agility relied on clean synchronization between engine, gearbox, and final drives. Assembly under power rationing meant more torque checks by hand. Dieter emphasized torque specs in training. He knew over-tightened bolts cracked housings, under-tightened ones backed out under vibration. Both happened more often when crews were tired or new. Field performance echoed factory decisions. Panthers that received full-quality bearings and proper heat treatment lasted longer. Those built during peak shortages failed sooner. Dieter read reports of Panthers arriving at the front and breaking down within their first marches. He traced those failures back to complexity meeting scarcity, high-spec components built with compromised materials and interrupted power. Complexity also meant each delay amplified. A missing batch of bearings did not stop just one station. It stopped every station downstream. A single design change rippled across welding, machining, and inspection. Dieter compared the Panther to a fine instrument that demanded a full orchestra and a quiet hall. Germany had neither by late 1943. By 1944, efforts to simplify some Panther features existed. Standardized wheels, minor plate thickness tweaks, but the core complexity remained. The machine still required tight tolerances, long welds, and precise gearboxes. Output remained limited. Total Panthers would end near 6,000. The Soviets and Americans would field a combined near 90,000 T-34s and Shermans. The numbers showed how complexity without resources loses the numbers game. Takeaway: the Panther's battlefield edge rested on intricate welds, tight gearboxes, and finely tuned assemblies. Those choices drove machining hours and tolerance demands that Germany's shrinking fuel, material, and labor base could not sustain at scale. For engineers and architects, the lesson is that performance gains built on complexity must be matched by industrial capacity, or they stay rare and fragile. Engines of the Panzerwaffe. At the heart of every German tank was a Maybach engine. By the late 1930s, Karl Maybach's company had become the sole designer of engines for Germany's new armored force. These were not the rugged, simple diesels of their Soviet counterparts. They were complex, high-performance gasoline engines, closer to aircraft power plants than tractor motors. They were marvels of engineering that promised high horsepower, but they also demanded respect, careful maintenance, and a steady supply of fuel, three things that grew scarcer as the war went on. The evolution of these engines tells a story of ambition and compromise. Early tanks like the Panzer II and III used smaller 6- and 12-cylinder Maybachs, producing between 140 and 300 horsepower. They were adequate for the light tanks of the Blitzkrieg era. But as German tanks grew heavier, their hearts had to grow stronger. The development of the Tiger and Panther tanks in response to the Soviet demanded a new class of engine. The first attempt was the Maybach HL-210. This 21-liter V12 engine was designed for the new Tiger tank, promising 650 horsepower. It was an advanced design with an aluminum crankcase and block to save weight, but it was rushed into production. The first 250 Tigers that rolled out of the factory were equipped with an engine that was not ready. It was prone to overheating and failures. The operational manuals urgently recommended that crews not push the engine past 2,600 revolutions per minute, well below its theoretical maximum. The Tiger, a 45-ton monster, was underpowered at birth. The solution was the legendary HL-230. Maybach's engineers took the lessons from the HL-210 and built a more robust engine. They replaced the aluminum block with a more durable cast iron one and increased the displacement to 23 liters. The result was a reliable 700 horsepower. The HL-230 became the standard power plant for Germany's heavy tanks, powering the later Tiger I, the Panther, the massive King Tiger, and the Jagdtiger tank destroyer. Nearly 9,000 of these engines were built. But even this powerful engine had its limits. It was a gasoline engine, and a thirsty one. A Tiger tank's operational range was severely limited by its high fuel consumption, a critical weakness on the sprawling Eastern Front. Gasoline also made German tanks far more vulnerable to fire than the diesel-powered T-34. A single penetrating hit to the engine compartment could turn a Panther into an inferno. Dieter, in his Augsburg workshop, knew the Maybach's two faces. He admired its compact power, the way it squeezed so much performance into a tight engine bay. But he also saw the consequences. He saw Panthers with watertight engine compartments, a design feature that inadvertently trapped leaking fuel and oil, creating a fire hazard. He saw the constant demand for high-octane gasoline, a strategic resource that Germany struggled to produce under Allied bombing. The German High Command was not blind to the advantages of diesel. Daimler-Benz, a rival to Maybach, championed diesel technology and even designed a version of the Panther with a diesel engine. But the German war machine was already tooled for gasoline. Shifting to diesel would have required a massive industrial effort, and diesel fuel itself was a strategic resource, jealously guarded by the German Navy for its U-boat fleet. So the Panzers ran on gasoline until the end. Late in the war, German engineers, desperate for more power, began to explore even more radical ideas. With the development of the first jet aircraft, some looked to gas turbines. A turbine promised enormous power in a compact size. A prototype was even fitted into a Jagdtiger, offering nearly 1,000 horsepower, a huge leap over the 700 of the Maybach. But the technology was in its infancy. The turbine drank fuel at an astronomical rate, and its exhaust was so hot it could set fire to nearby trees, a tactical nightmare. Like so many of Germany's late-war wonder weapons, the turbine-powered tank arrived too late and with too many problems to make a difference. The story of Germany's tank engines is the story of a gamble on technological superiority. Maybach's gasoline engines gave German tanks a power-to-weight ratio that, on paper, was often superior to their Allied counterparts. But that performance came at a cost in fuel, reliability, and fire risk. While Soviet industry churned out thousands of simple, robust diesel engines, German engineers chased ever higher performance from a complex and demanding technology. The heart of the Panzerwaffe was a thoroughbred racehorse engine in a war that was ultimately won by workhorses. Takeaway: Germany's reliance on complex, high-performance gasoline engines from Maybach provided impressive power, but came with critical trade-offs in fuel consumption, reliability, and fire risk. The decision to forego simpler diesel technology, used effectively by the Soviets, reflected a broader German engineering philosophy of pursuing technical perfection over mass-producible ruggedness, a choice that had significant strategic consequences. A war of blueprints. The battle for Germany's armored supremacy was not just fought on the Eastern Front or in the deserts of North Africa. It was also fought on drafting tables and in factory boardrooms. The development of Germany's most famous tanks, the Tiger and the Panther, was marked by intense internal competition, driven by rival engineering philosophies, corporate pride, and the direct influence of Adolf Hitler. The story of the Tiger tank is the story of a duel between two of Germany's most prominent engineering firms, Henschel and Porsche. By 1941, the German army needed a new heavy tank. Both companies were tasked with designing a 45-ton vehicle capable of carrying the devastating 88mm gun. Both had to use the same Krupp-designed turret. The competition came down to the chassis and the engine. Henschel's design was conventional. It used a traditional hull layout, a powerful Maybach gasoline engine, and a proven mechanical transmission. It was a conservative, low-risk design that built on Germany's existing tank-building experience. Ferdinand Porsche, on the other hand, proposed something far more radical. Porsche was a brilliant but eccentric engineer, always drawn to the most complex and innovative solution. His design for the Tiger, the VK45.01P, featured a revolutionary gasoline-electric drive. Two air-cooled gasoline engines powered electric generators, which in turn powered electric motors that drove the tracks. In theory, this system eliminated the need for a complex mechanical transmission and offered smooth, variable speed steering. Porsche was so confident in his design that he ordered the production of 90 chassis before the trials were even complete. On Hitler's birthday in April 1942, both prototypes were demonstrated for the Führer. Hitler was famously fascinated by Porsche's high-tech, wonder weapon approach. But during field trials, the Porsche Tiger failed spectacularly. Its complex electric drive was unreliable and prone to breakdowns. It consumed vast amounts of copper, a strategic material Germany could ill afford. The more conventional Henschel design, while less ambitious, proved to be far more reliable and easier to manufacture. The Henschel proposal was chosen, and its chassis would become the basis for the legendary Tiger I. Porsche's 90 pre-produced chassis were not wasted. They were converted into heavy tank destroyers, armed with an even more powerful 88mm gun. They were named Ferdinand, in honor of their creator. These machines, later renamed Elephant, were formidable defensive weapons, but they were plagued by the same reliability issues as the prototype Tiger. They famously went into the Battle of Kursk without a single machine gun for self-defense, a critical oversight that made them vulnerable to Soviet infantry. A similar battle of blueprints was fought over the Panther. The appearance of the Soviet in 1941 was a profound shock to the German army. Its sloped armor, wide tracks, and simple, robust design were revolutionary. In response, Germany launched a crash program to develop a new medium tank. Two firms, Daimler-Benz and Maschinenfabrik Augsburg-Neuenburg, submitted proposals. The Daimler-Benz design was a near-direct copy of the T-34. It had the same hull shape, rear-mounted drive, and a diesel engine. It was a pragmatic, if unoriginal, response to the Soviet threat. Hitler, impressed by the T-34's effectiveness, initially favored the Daimler-Benz proposal. The MAN design, however, was a more traditional German interpretation. While it incorporated the sloped armor, it had a more complex torsion bar suspension, a forward-mounted transmission, and a higher profile. Crucially, MAN's design could accommodate the existing turret designed for the Tiger, which promised to speed up production. A special commission, weighing the risks of developing a new turret and engine for the Daimler design, chose the MAN proposal. It was a compromise between innovation and industrial reality. The MAN design became the Panther, a tank that combined the best of German and Soviet design philosophies, but one that was also more complex and difficult to produce than the T-34 it was meant to counter. This internal competition, while fostering innovation, also contributed to the German war machine's weaknesses. The constant pursuit of the best design, often encouraged by Hitler's fascination with technology, led to a proliferation of different models and variants. This lack of standardization created a logistical nightmare, making it difficult to produce tanks and spare parts in the vast quantities needed to win a war of attrition. While the Soviets focused on refining and mass-producing a single, good-enough design, the T-34, the Germans were often still arguing at the drawing board. Takeaway: the development of Germany's key tanks was shaped by a fierce internal competition between designers like Porsche and Henschel, and companies like MAN and Daimler-Benz. This rivalry, fueled by different engineering philosophies and political influence, spurred technological innovation, but also led to overly complex designs, a lack of standardization, and production delays that ultimately hampered the German war effort. Tiger heavy ambition. The Tiger I embodied heavy ambition, over 100 millimeters of frontal armor, a fearsome 88 millimeter gun, and interleaved road wheels that spread weight. It also embodied industrial strain. At 57 metric tons, the Tiger taxed bridges, rail cars, and its own drivetrain. Its interleaved wheels trapped mud and ice, driving maintenance hours up. The Maybach HL210 and later HL230 engines struggled with the load, especially when fuel quality dropped. Machining the Tiger was slow. Its armor plates were thick and flat, easier to weld than the Panther's slopes but heavier to handle. The turret's massive gun mount required careful balance. Gearboxes and final drives suffered under the torque. Breakdowns on road marches were common. Only about 1,300 Tigers were built, a fraction of what battlefield demand wanted. Each Tiger consumed materials and labor that could have produced several Panzer IVs. Recovering a broken Tiger was a mission by itself. The standard 18-ton recovery half-track could not tow it alone. Manuals called for 3 of them chained together. If a unit lacked that many, crews sometimes used another Tiger to tow the dead one and burned out the towing Tiger's transmission, trading one immobile tank for 2. Field memoirs recall Tiger crews loving the gun and fearing the march to the front. Reliability lagged far behind firepower. For Dieter, the Tiger is a lesson in weight versus sustainment. A machine that could dominate a duel but too often arrived late, short in number, or sidelined by its own mass. Takeaway: the Tiger delivered shock power through armor and gun, but its weight, complex wheels, and strained drivetrains made it a maintenance burden that Germany's shrinking industry could not support in quantity. Tiger II overreach. The Tiger II, or King Tiger, pushed German heavy design to its limit. Front armor over 150 millimeters thick and a long 88 millimeter gun gave it immense protection and reach. But at nearly 70 metric tons, The tank overmatched its final drives and gearboxes. The same Maybach HL-230 engine that powered Panthers had to move far more mass. Power to weight dropped, and reliability followed. Production never caught up to ambition. Only about 489 Tiger IIs were built. Each required extensive machining on thick plate, precise turret balance, and heavy transport arrangements. Final drive failures and transmission issues plagued early units. Fuel consumption was severe at a time when fuel allocations were already cut by roughly 1/3. Rail movement demanded special wagons. Road movement chewed up tracks and roads alike. In off-road combat conditions, a King Tiger could drink roughly 500 liters of gasoline to cover 100 kilometers. With the Luftwaffe grounded for lack of fuel, moving a battalion of Tiger IIs became an economic disaster. Crews abandoned some simply because the tanks ran dry, leaving 70-ton fortresses silent on the roadside. Memoirs describe Tiger II crews confident in armor, yet wary of marches. A breakdown often meant abandonment because recovery assets were limited. Dieter saw the Tiger II as a case study in overreach. Technical excellence on paper, but unsustainable in a bombed, fuel-starved economy. The tank was nearly invulnerable from the front. Its logistics were not. Takeaway: the Tiger II's mass and complexity created a tank that outperformed Allied guns head-on, but collapsed under its own logistical weight. Industrial overreach turned a formidable design into a rarity with frequent mechanical failures. Numbers game lost. The ledger tells a blunt story. Germany's top 3 tanks by volume were the Panzer IV, the Panther, and the Tiger I. The Panzer IV reached more than 8,000 units. Panthers stopped around 6,000. Tigers halted near 1,300. Allied output dwarfed those totals. The Soviet Union built about 50,000 T-34s. The United States produced roughly 49,000 Shermans. Even before counting British and Canadian armor, the ratios were brutal. Monthly rhythms show the gap. In some months of 1943, Panzer IV production across factories passed 300. Panther output in the same period often sat in the tens. Tigers rarely broke double digits per month. Soviet plants in the Urals pushed hundreds of T-34s weekly, even through winter. American lines rolled Shermans steadily with few interruptions from bombing. Industrial structure explains part of it. German plants operated under bombing, fuel cuts, and material shortages. Precision-heavy designs like Panthers and Tigers soaked up labor hours and bearings that were already scarce. The Panzer IV, simpler and lighter, moved faster but still could not match Allied volume. Meanwhile, Soviet factories used simpler welds, looser tolerances, and vast coal and steel supplies. American plants enjoyed intact railroads, stable power, and abundant copper and rubber. On the battlefield, these numbers translated into presence. A Panther could dominate a duel, but there were fewer of them. Panzer IV units stayed more numerous but increasingly outgunned. Tigers brought shock but appeared in handfuls. Opposite them, T-34s and Shermans arrived in waves, with spares and recovery crews behind them. Commanders fought with what the factories could send, and the factories sent far more steel east and west than Germany could. Money mirrored the gap. A Tiger I cost roughly 250,000 Reichsmarks. A Panther cost about 117,000. A Panzer IV cost roughly 103,000. One Tiger equaled 2.5 Panzer IVs. The Allies treated tanks almost like ammunition. If a Sherman broke, a new one arrived, while German crews nursed transmissions with whatever tools and luck they had. Takeaway: Germany fielded 3 key tanks, Panzer IV, Panther, and Tiger I, but their combined output was eclipsed by Soviet and American volumes. Industrial capacity, not just design quality, decided how many machines reached the front. In that numbers game, Germany lost. Lesson of industry. Dieter returned to the factory one night and found a new Panther stranded outside. Its engine had seized from faulty bearings. He wrote, "We could design excellence. We could not escape reality." Takeaway: Germany's engineering brilliance could not overcome its collapsing industrial base. Talent alone does not win wars. Sustained production, materials, and stable logistics do.